All right, well, I'm just going to get started and assume that it's working. Maybe I'll show my screen. I'm going to go to the top of the questions. I looked at them and I didn't know how to organize them, so I'm really just going to start at the top and work my way down, and we'll see where it goes from there. As I understand that when we dissolve something in water, it becomes aqueous, but sometimes we call a compound solution ionic compound aqueous when water isn't involved. How can we determine which is aqueous then, and why would it be considered aqueous? Aqueous is only something that is dissolved in water. So there's a lot of times when it'll actually give you the compound, it'll already be dissolved in water. That's when it looks like it's already a solution. So solution is kind of a fancy word for dissolved in water or made some sort of liquid mixture. So aqueous can only be defined as when you dissolve something in water. And how can you determine if it's aqueous? You can determine if it's aqueous because it looks like a liquid, but it's an ionic compound. Ionic compounds, in order to be a liquid, would have to be really, really hot. And we just don't deal with those like it's freakishly hot. So if it's an ionic compound, which is a metal and nonmetal, and it looks like a liquid, it has to be aqueous. Otherwise, if it's a molecular compound, it looks like a liquid, then it's most likely a liquid. Does it always have to be a liquid? No, not always, but that's the guess I would probably go for if you don't know for sure. So that would be the difference. On to the next one. We have mostly been working with 2 reactants and determine the results based off of that. What if there are 3 or 4? How do we determine products and type? If there are 3 or 4 reactants, then you're looking at a reaction that we are not going to cover in this class. That would be an AP topic and even past that. So you won't have to worry about that. It'll be 2 reactants at the most. Otherwise, you won't be asked to predict the products. I'd have to give you the entire reaction. All right, to the next one. Since I was struggling with writing ionic and kinetic equations, I searched practice problems and completed some. Good work to you. And I realized that everything in that worksheet was aqueous makes aqueous a solid. Yes, that's usually the case. It doesn't always. In order to have a net ionic equation, it has to end with a solid, a liquid, or a gas. It can't end in aqueous. Because if you just have all aqueous and making all aqueous, then you really didn't make anything at all. So is there a reason for the aqueous part? When you have a reaction happen, if you had solids, if you took like this solid and like a white powder and another white powder and you try to mix them together, the atoms don't really mix because one like grain of white solid powder is really a bazillion atoms. So you can't ever get like this white powder's atoms right next to this white powder's atoms and actually have them next to each other so that they can react. So we use aqueous because aqueous separates it into its ions. And once it's in its ions, then this atom can meet the other reactant's atom and they can actually react. While if you have 2 solids, they can't actually do any kind of combining. So it's kind of impossible. So that's why we always have aqueous. They actually make a reaction happen faster. Could 2 solids react? Sure. Not all of it's going to react though because the 2 atoms can't meet and it's going to be really slow. So most often we always use aqueous things. Once you liquefy things, things can move, and when things can move, they can react more easily. So that's the answer to that one. Onward to the next. Is type of reaction combustion when oxygen is included? Technically, yes. When oxygen is included as a reactant, it is technically called a combustion reaction. Continue on the question. Is there any other rules to be a combustion reaction? It's somewhat confusing since I remember hearing something like it's combustion when products are H2 and CO2. So the most common type of combustion reaction will include some sort of carbony compound. Maybe I can go to my other screen for this part. I will try 2 screens too. Oh, are you seeing like a good screen? Okay. I'm going to go find my paint feature. Okay. So a combustion reaction is technically anything plus oxygen will be a combustion reaction, but it always has to be that way. But the most frequent kind that you'll see, 99, not 99, but at least 90% of the time, is going to be some sort of carbon hydrogen thing. Sometimes oxygen, but not always, will combine with oxygen, and it will always make a CO2 plus H2O products. So that's why I gave you this definition of combustion reactions, because they cover about 90% of the combustion reactions that you'll ever really see in your everyday life. It'll have some sort of carbon hydrogen thing, sometimes a no, you don't have to, but it will always include oxygen as reactant, and it'll always make CO2 and H2O. So by technical definition, the top is the only requirement, the oxygen part, the top thing I wrote here, but most often it's the bottom part, so that's why we talked about it. All right. Going on to the next question. This person is trying to fix it, I think. What if it is oxygen, hydrogen, or water, carbon dioxide, and something else? Would it be combustion then? I do not understand that person's question. So I'm going to put that there, and I'll come back to it at the end, and hopefully somebody will have asked something. Okay, to the next one. To use a solubility chart to see which one is a precipitate and which one is aqueous. Yes, but when word equation of reactant part is given and the state of matter is not there, can I use the solubility chart to see what state of matter it is? Yes, but only when it's an ionic compound. The solubility chart only includes ionic compounds, and it only includes them as a solid or aqueous, because really as a liquid it have to be freakishly hot, and you know it anyway. So really you can only use a solubility chart to know for ionic compounds. But yes, you can use it for that. Do the next one. I get that electronegativity has to do with reactants and products, but what does ionization energy have to do with any of it? Ionization energy is directly connected to electronegativity. So electronegativity is how much you love electronegativity is how much you love electrons. So if you really love electrons, then you're not going to want to give them up. And ionization energy is the amount of energy needed to remove an outer electron. So the higher the electronegativity, the more you love electrons, the harder it is to remove an electron, which means a higher ionization energy. So higher electronegativity will relate to a higher ionization energy. So anytime you use electronegativity, you can really talk about ionization energy too, because they were directly related. Okay, I think someone might have a question there, but not really sure. If you do, you let me know. I'll look back or kind of jump into where I am here in the document. Alrighty. Okay, if something looks like it is a liquid and it's molecular, is it always a liquid or could it be aqueous? It could be aqueous, but most often it's a liquid, but it could be aqueous. Sometimes liquids are aqueous when water is not dissolved. Is that just for ionic compounds or molecular? Sometimes liquids are aqueous when water is not dissolved. Is that just for ionic compounds and molecular too? If it is for molecular, how would we know? If it is, I'm trying to understand this question. Sometimes liquids are aqueous when water is not dissolved. Aqueous doesn't mean when water is dissolved. So aqueous means water does the dissolving. Water isn't dissolved. I think this person for this question is kind of just wondering, like, if it's a molecular compound, how would you know if it's a liquid or aqueous? by looking at it, if you don't have more information, you may not know for sure, but I would totally go for, if I see it's molecular, it's going to be a liquid. If it looks liquidy, is it 100% the case? No, because we had hydrogen peroxide. That was ionico. Can't think of an example that we used in class, but yeah, there's tons of examples. Like you could take ethanol and alcohol and put it in the water. That would be a aqueous situation, but it would look like a liquid. So to this person, you really wouldn't know, but I can't answer that question very well. Most likely liquid, but doesn't have to be. Okay, I'm going to move upward to the person's at 824. As they said that they fixed it, which is great. What if the product is carbon dioxide and water? Would it be combustion then? If you have the products of carbon dioxide and water, and they are just those products, but you don't have oxygen as a reactant, then I can't say that it's combustion. I don't know exactly. I can't think of an example where carbon dioxide and water are products and it's not combustion. It doesn't come to mind. If those are the sole products, like there's a common, like in your review worksheet, we made NaCl, carbon dioxide, and water, and those three things were products. And that wasn't a combustion reaction. That was a totally different type of reaction we haven't covered. But to just have carbon dioxide and just water, I would have to guess it's most likely combustion. But if I didn't see an oxygen as a reactant, then I wouldn't say it's combustion. So you've got to have oxygen as a reactant. Then I would say combustion for sure. Okay. Ooh, the next one. I got a lot of questions here. I'm kind of blowing through them fast. I hope that's okay. What if the products are carbon dioxide? Oh, they just put it down here again. Okay. For objective 8, do we just have to know how to read the chart on the back of the periodic table? Yes, as long as you know what the words soluble and insoluble, or it says not soluble mean, you should be good. Not soluble means it's solid. Soluble means it's dissolved in water or aqueous. So yes, you just have to know how to read the chart. For objective 3, does that just mean we have to understand that when an atom has a high electronegativity, it doesn't like sharing, so it creates a reaction where it can share less electrons and can pair with a lower electronegative atom so that it can pull electrons closer to itself? I would say that's a great example on why one reaction might happen. Is it the only reason that any kind of reactions happen? No, but that's a great example on why a reaction would want to happen. That seems very logical. You have to look at the reaction itself and see how they're sharing electrons. You'd have to look at the reaction and maybe you could see that the according to the electron configuration, this one isn't fully octet happy, but then after the reaction it is. So objective 3 is kind of covering all of those parts. Like if you could look at all the periodic trends, ionization energy, electronegativity, and electron configuration and come to some sort of consensus, that would be objective 3 is looking for. I believe there's a question down here from the review worksheet. This one here, so I'm going to pull that up. Okay, I pulled up the question from the review worksheet that has to do with nitrogen and hydrogen. It says, could you explain the question from the review gave involving nitrogen and hydrogen where we have to explain why the reaction would occur? Let me go to screen sharing here instead of just seeing my lovely face. Okay. All right. So in this reaction, if you have nitrogen plus hydrogen, it can make NH3, which is ammonia. If I balance the equation, it would look something like this. And the question is saying if you had to use electronegativity or ionization energy or electron configuration, could you reason why this reaction would occur? So I'm going to draw what the molecules look like. That's a great place to start. N2 has a triple bond. You draw the Lewis dot structure. Hydrogen has a single bond. And NH3 has bonds that look like this. Okay, and this 2 part just really means that there are 2 of these. Not that they're attached to each other, but that there's 2 NH3 molecules. I didn't have to draw both of them, but I think you kind of get the idea. Okay. All right, so if we take a look at, we'll start at the bottom actually. If you take a look at electron configuration, so here is nitrogen, and you really kind of want to take one atom at a time. Is nitrogen octet happy? He totally is. He has a full electron configuration. He's just like a noble gas. Things are looking good. I know this because he has 1, 2, 3, 4, 5, 6, 7, 8 electrons around him. If I go over here and look at this nitrogen, he has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around him, so he is also octet happy. So to him, the reaction, according to electron configuration, it really doesn't matter which way he goes. He's fine with it. If we take a look at hydrogen, he has 2 electrons, and for him, that's all he needs to be in order to be a noble gas, because then he's like helium. So he's octet happy too. And hydrogen over here has 1, 2 electrons, because he's sharing 1, so he's also octet happy. So according to electron configurations, this reaction doesn't really have any benefit going on for it. So if we take a look at electronegativity, which I think is everyone's favorite, electronegativity is really how much you love electrons if you're an atom. Taking a look at nitrogen here with the N2, nitrogen has to share 3 electrons. Nitrogen between the 2 really, really loves electrons. And if we look at hydrogen, he has to share 2 electrons, or sorry, he has to share 1 electron to get to 2 electrons, and he doesn't really like electrons between the 2. Does hydrogen love electrons? On the scale of 0 to 4 of electronegativity, he loves it at a 2.1. Nitrogen loves it at like, I think, a 3.4-ish or something. So I can look on the periodic table and I can know that hydrogen loves electrons less than nitrogen. You don't have to know the exact electronegativity, but you do have to know which one loves electrons more than the other. So nitrogen loves electrons. Right now he's sharing 3 electrons with each other, and he's sharing them equally. If we go to this other side, as NH3, N is still sharing 3 electrons. So that kind of seems like, okay, there's no real benefit for him going from left to right. But what he's also doing is he's sharing the electrons unequally. In other words, he's got his 3 electrons, and he's holding on to them majority of the time because this is a polar bond. He's not only holding on to his 3 electrons that are right by him, but he's also hogging the electrons of hydrogen. So in this way, nitrogen's got a good thing going for him. He not only has his 3 electrons by him all the time, he's also gaining slightly the hydrogen's electrons. They happen to live around him more often, or towards him more often. In that way, he's kind of gained electrons. To him, who loves electrons, nitrogen is very happy about this reaction. So that's his benefit for this reaction. That's why the reaction would happen, because he gets something out of the deal. Hydrogen, we know, doesn't really like electrons, so he's totally okay with kind of giving up his electrons. He's fine with it. It sounds like a good deal to him too. So overall, this reaction kind of gives hydrogen and nitrogen a good benefit. You can kind of take the same idea with ionization energy. Ionization energy is the amount of energy needed to remove an outer electron. Now in this case, we're not actually removing any outer electron, so you could talk about ionization energy, but it's kind of a stretch. I think with ionization energy, this would be a time when you probably don't want to talk about it because you're not actually losing electrons. So no electrons are really lost, not unless you have an ionic compound that's being made. That's when you give and take electrons. Here they're semi-lost, but really not fully. And ionization energy is technically by how do you fully lose an electron. So I wouldn't talk about ionization energy here either. So there's a case where it doesn't really go hand in hand. Electronegativity and ionization energy. All right. Back to me. I'm going to go back to the question screen. I think. There we go. question was, are combustion reactions at approx always H2O and CO2? No. I'll put it at 821. Technically, combustion reactions occur anytime that you have oxygen as a reactant. And so you could have something like we did in the lab was magnesium plus oxygen, magnesium oxide. That's a combustion reaction. It doesn't make CO2 and H2O. But like I talked about, 90% of the time it does make CO2 and H2O when you deal with some sort of carbon-hydrogen thing. So that's why we talked about that with combustion reactions. But no, it doesn't always have to make CO2 and H2O. That's just the most common. Okay. Could you go over a single replacement and double replacement reaction? I'm confused on how to determine the products. Okay, sure. I will show you my screen. And then you want an ionic and kinetic equation, so I'll do that too. Okay. Let me screen share this. Okay. Oops, that's what the screen is. All right, a single replacement reaction. That would be something like NaOH plus calcium. So in this case, I have Na as a 1 plus and hydroxide as a 1 minus. Calcium is an atom, so technically he has no charge at all. He's just an atom. He has the same number of protons and electrons, so things look good. But in a single replacement reaction, one replaces the other. This calcium will come in and hook up with Na or OH depending on what he's attracted to. So on the other side, calcium is going to be attracted to Na or OH. And if calcium is going to have a charge, he has a 2 plus charge. So calcium has a 2 plus charge is going to be attracted to the negative ion. And he's going to replace the sodium ion. So now calcium is hooked up with hydroxide. Hydroxide being a 1 minus, calcium a 2 plus, which means I need CaOH2. I need 2 hydroxides to balance out my 1 calcium. And what that does is leave sodium left over. Sodium being an atom, he doesn't have a charge. He's not an ion, he's just an atom. That would be a single replacement reaction. To finalize the equation, I'd want to balance it by noticing I have 2 hydroxides on this side, so I have to put a 2 in front of my NaOH, which creates a 2 for my Na. There is a single replacement. Double replacement. If we had something like calcium chloride plus, well, we'll do a tricky one, like an aluminum sulfate? Sure. That one looks good. Okay. So here I know it's a double replacement reaction because I can see that there's a compound plus a compound. That's entirely different than the single replacement, which is compound plus an element. So double replacement reaction is the one with that will have a compound plus a compound. I think it's helpful in this case to put in all your ion charges. So according to the periodic table, calcium is a 2 plus, chlorine is a 1 minus, aluminum is a 3 plus, and sulfate is a 2 minus. And then they're just going to kind of do a double switcheroo. Like my positive guy, my aluminum 3 plus, is going to want to hook up with the other negative guy, my chlorine. Now I know that they've got 2's with both of it, but don't take both of the 2's. Just take the ion itself. This is the aluminum 3 plus ion and the chlorine 1 minus ion. Remember in solution, it's not that the 2 Als are stuck together. It's that one Al is swimming around by itself and the other aluminum is swimming around by itself. They're not really attached, so I don't want to take both of them with me. I'm going to take one of each ion, aluminum 3 plus, and my chlorine 1 minus. Now I can see that 3 plus and 1 minus aren't so good, so I'll have to put a 3 there to make it bounce out. And then the other thing happens, my calcium is now going to hook up with my sulfate. Calcium, being a 2 plus, is going to hook up with my sulfate, SO4, which is a 2 minus. So there I can see I've got a plus 2 and a minus 2, and they are happy that way. Yes, I know there's 3 sulfates, but remember they're not hooked up together. They're all swimming around by themselves, so we only take as many as we need. In the end, I have to balance the equation. I guess I'll start with, I don't know, sulfates. There is only one sulfate on the right, and there's 3 sulfates on the left. So I'll need 3 here, 3 sulfates, which then create 3 calciums. So I'll need 3 calciums on the left. I now have 3 calciums on the left, but I created 6 chlorines, so I'll need a 2 on the right to create 6 chlorines. Makes 2 aluminums and things look good. Okay. I think the next question was about here it is. An ionic and a nenic equation. That's what I was thinking. Okay. 843. So I'm going to use, I could just use this calcium sulfate one, but I'm going to use green. I need to write more. Okay. Okay, so I'm going to use that calcium. Oh, I didn't use, I gotta check my solubility chart. Hold on here. I don't know if I can really use that one. It's calcium aluminum sulfate. It made calcium sulfate. Oh, that's perfect. Okay. Yeah, that works out nicely. Okay. Calcium chloride plus aluminum sulfate. Whoop. Made calcium sulfate. Oop, I did it opposite this time, but that's okay. Aluminum chloride. Okay. All right, so I'm going to use my solubility chart. This is my double placement reaction. I'm going to go in my solubility chart, which I have right here, and I'm going to look up first my calcium chloride. So if I look up chlorine, and I go over and look up calcium, which is in all others, I can see it's soluble. Soluble means it's aqueous. So this one is aqueous. I'm going to look up my aluminum sulfate next to get its state of matter. So my sulfate is in the middle. My aluminum would be all others, and it also says it's soluble. I don't know if you can see my pen there, but we'll go with it. So that's aqueous. I'm going to look up my calcium sulfate next. So go to the middle again and find my sulfate. And I look up, I see calcium, and I see it's not soluble, which means it's a solid. So that one's my solid. And if I go to aluminum chloride, chlorine attached to aluminum, which is in all others, is soluble or aqueous. So it just happened nicely that I picked some. Okay, so if I wanted to write the ionic equation, I have to separate anything that's aqueous. Anything that's aqueous must be separated because aqueous means that the water swooped in, surrounded the ions, and separated them into their ions. Anything that's not aqueous means they're still together. So I want to separate it into their ions. So it might be easier to put in the charges for each ion here. Three plus and 1 minus. So I'm going to trust that on the periodic table. You can use your ions. And then I'm going to start writing my ionic equation. This one's my aqueous, so I have to separate it. Calcium 2 plus is my ion. It is aqueous, and I have a total of 3 of them. So I put the big 3 up front. Plus chlorine, 1 minus, it's my next ion. It's also aqueous, and I have a total of 2 times 3, 6 of them. It's not that the chlorines are attached to each other. It's that chlorine is my ion. Cl1 minus is my ion. Cl2 1 minus is not an ion. It doesn't exist. I want to write down the ion first, then count how many I have. So go to my next one. It's aqueous, so I need to separate it. Aluminum 3 plus is my ion. How many do I have of them? 2 of them. So I put the 2 out front. Aqueous. Plus SO4 2 minus. That's my ion. It's aqueous. How many do I have of them? 3. Makes, this one's a solid, so I'm going to write it exactly as it is. Don't change anything. Plus, let me go down the line here. Aluminum 3 plus is my ion. it's aqueous. And how many of them do I have? 2. Plus chlorine, 1 minus, is my ion. It's aqueous, and I happen to have 3 times 2, 6 of them. All right, that would be my ionic equation. It shows all the ions, or aqueous things in solution. To a net ionic equation, that's when we want to find spectator ions. Spectator ions are the things that look the same on the left and the right. Like my chlorine is a spectator ion. It looks exactly the same on the left and the right. My aluminum is exactly the same on the left and the right. Everything else is different, so those are the things I want to include in the net ionic equation. So I just want to write down everything it says in my ionic equation, except for those ones I circled, because the ones I circled are the spectator ions. The net ionic equation actually shows what happened. What actually happened was that calcium is now hooked up with sulfate, and it made a new solid. That's an actually new thing that happened. Yes, aluminum kind of hooked up with chlorine, but not really because they're aqueous, so not fully stuck together. It's just we put them together to kind of make them balance out. So there you go. Where's my mouse? Here it is. Make sure. Oh, bother. I do not know if I'm going to get to all these equations. How do we know when to split ionic equations? When they're aqueous, you have to split them. Okay, well, let's just keep going and see how far I get. Can you give an example of a good equation? I think there's a question down here too. A good question, rather. So, if we go to your labs. I'm not saying these are the best questions. You can see an excellent question will be ask complex questions that relate to the topic of study, which can be answered through data collection. So data collection is the key part there. Like, could you decide what independent and dependent variable you need to answer this? And the question also kind of has to relate in some way to your background information. You can't just ask a random question that doesn't relate to anything you've learned before. So in this synthesis reaction, my first one, you can see my observations. They don't directly go with my questions. They don't have to. My first question says, if E equals mc squared, this is my prior knowledge. That's something I think you guys have heard about with Einstein, that deals with energy turns into mass, and mass could turn into energy. And I made a bright light here, so I was thinking, is the energy I see made from mass being destroyed? Because mass being destroyed can create energy. So in that way, could I find data for that? Yep, I could look at the mass before, and I could look at the mass after, and I could actually kind of determine if mass was destroyed. My second question was, the white stuff is powdery. So did it all react, or is there still silver, magnesium left over? It's a terrible question, Sarah. I wouldn't call it a very good question. What would I give that one? It doesn't really relate to background information very well. Maybe I could talk about the ionic compound a little bit better, being the white stuff. And could I answer it through data collection? Not very easily, unless I could somehow separate it. So I would give that more of like a C answer, because I can't easily answer it through data collection. And it references things, but very minimally. So that's a C question. My third one, atoms glow colors because of where the electrons move. So what were the individual electron jumps that made this color? I would have to do a little bit better with that question. In other words, Could I get data to actually know where the individual electrons jump? Yes, it's possible. Do we have the equipment for that? No, but we could. I would want to use, is that good enough maybe? We could tell where the electrons jump by looking at the spectroscopes, and the spectroscopes could tell us the individual bands of light, and the individual bands of light would tell us the wavelength. And the wavelength could in the end tell us the energy jumps, which could, in the end, if we knew the atom's exact structure, tell us where the electrons moved. So yes, in theory, we could use data to do that. So I guess I would have to give that an A question, an A answer. I hope that helps. I just kind of analyzed my 3 questions. I give myself an A, a C, and an A. Other levels of solubility, more or less soluble, or simply soluble insoluble? Yes, there are different levels of solubility. That's a second semester topic that we may or may not get to this year. At this point, you just have to know it's soluble or insoluble. And as you can see on your solubility chart, it kind of gives you a little reference there on what that means if you're really curious about it. Can you see my screen right now? I don't even know. Yes, you can. Okay. On your solubility chart, it says more than 0.1 moles will dissolve per liter. So that's the level of solubility. Do you have to know that? No. I'm just going to look for soluble versus insoluble. Are there 2 types of equations? As in, there's an equation about synthesis, combustion, decomposition, or synthesis. For example, on the practice lab we did together as a class on Friday, are you talking about the egg demo? And the reactions were a single replacement and the products turned into synthesis? Yes. There were 2 types of equations there because there were 2 steps to the reaction. The first step of the reaction was me reacting zinc with hydrochloric acid, and that happened in the flask. And then I took the products from the flask and I piped them into the egg. The hydrogen gas went into the egg, and that's where the synthesis reaction happened. So I did 2 different equations. One happened in the flask and one happened in the egg. All right, how do you know from the solubility rules chart that H3PO4 is soluble? That one's a tricky one because it's an acid, and we haven't covered acids yet. So if you look at phosphate being here, and he's hooked up to all others, you would assume it's a solid and not soluble. And if you wrote that on the test, I'd have to be 100% okay with it, because that's fine. But technically it's an acid, and acids dissolve in water. That's something you wouldn't know, so I wouldn't be putting that on the test. Sometimes it gets by me and I put it on a worksheet accidentally. I apologize for that. Can you explain what we have to know for objective 2? I can identify where atoms are going during the reaction. That one is covered kind of like in these questions here. So if you look on the review worksheet, that first slide, that's where you'll find that part. It's about precipitate lab. For NaOH and BaCO2, I got a precipitate, but according to solubility rules, NaCl is soluble and BaOH is also soluble. Is the result wrong? Yes and no. I'm just going to check your solubility chart. And NaCl is definitely soluble. Barium hydroxide is a solid. So let me check your question. So that right there is where you're reading the solubility chart wrong. Barium hydroxide, hydroxides are here. Barium is an all other situation, so it is not soluble. Barium hydroxide is a solid. So yes, you're reading the solubility charts wrong. Could you explain about the pink sheets, objective A through B, number 6 and 8? I kind of don't get what the difference is between the two, 6 and 8. Okay. Okay. In a balanced equation, the number of ions on the left and the right are the same. Sometimes this is true, but sometimes it isn't. Like, if you look in this equation here, the number of ions on the left and the number of ions on the right are the same if you consider that they don't have to be aqueous ions, because I have a total of 3 calciums on the left and a total of 3 calciums on the right. I have a total of 6 chlorines on the left and 6 chlorines on the right, but it doesn't always have to be true. A balanced equation isn't balanced because the number of ions are the same. An example of that would be this one right here, this equation. On the left side, I've got lots of ions. I've got 1, 2, 3, that's 3 ions, 4, and 5, but twice as much, 6, 7. I have 7 ions on the left, but I only have 1, 2, 3, 4, 5, 6 ions on the right. So the number of ions don't have to be the same in order to have a balanced equation. That's not a requirement of a balanced equation. Number 7, in a balanced equation, the types of states of matter and reactants and product sides are the same. No, that's not true either. If you look in this equation, aqueous on the left, aqueous on the left, 2 aqueous, but on the right side, I've got a solid, I've got an aqueous, I've got a liquid, I've got a gas, I've got all different things here. So you don't have to have the same states of matter on the left and the right. That's not a requirement of the balanced equation. Oh, you asked number 8 though. Number 8, in a balanced equation, the number of atoms are the same on the reactants and product side. That is true. So going back to this one, the number of ions aren't the same, but you always have 1 calcium on the left, 1 calcium on the right. 2 chlorines on the right or left, 2 chlorines on the right. You can still count atoms and make an atom inventory list on the left and the right, and those are the same. You have to have the same number of atoms. What about objective? C, is this just synthesis? It doesn't have to be just synthesis. It's got to, I'm going to ask only synthesis ones. So yes, because I wrote that there. Yes, and the one on the test is synthesis. So yes. And by trends, do you mean ionization, energy, electron configuration, and electronegativity also? Yes. How do you draw reactants and products in a beaker? Okay. 59. I'm going to draw it for this picture. How do I gotta erase them, it looks like. I'm going to draw a very fat beaker on the right. So here's my really fat beaker, and it's got water in it because all these reactions are done in aqueous. And so on the other side, what I can see that I actually did, according to my balance equation that I've already written, is that I made a solid calcium sulfate, which I can see also here in the ionic equation, and I also have 2 ions floating around in solution. So I could draw that by drawing calcium sulfate here as a solid. I'd want to draw them together because they're a solid. And I'm drawing 3 of them because I made 3 of them in this equation. I'd also want to draw that I've got aqueous things. I've got aluminum, 3 plus is aqueous, floating around. I want to draw 2 of them because in my ionic equation I draw 2 of them, it says. And I've got 6 chlorines. Ooh, my beaker's not big enough. 1, 2, 3, 4, 5, and 6. So hopefully you can see that in there. I've got my aqueous things. They're the products. They're floating around by themselves. And I've got my 3 solids being made. That would be how I would draw it in a beaker. Solids sit at the bottom, and the aqueous things float around on top. With hints of balance equation, why do you have to box in the polyatomic ions? You don't have to. It just makes your life a little bit easier, but there's no way you have to do that. What does the triangle heat have to do with balancing equations? It doesn't have anything to do with actually balancing equations. It just allows you to know more information about what happened in the reaction. I'm not going to grade for that, but I wanted to kind of tell you about what those things are and how that means, in case you've seen it before, and you'll probably see it again in the future. So we thought we'd talk about it. You have to remember Dr. Hofbrinkel. Yes, you're going to have to know Dr. Hofbrinkel. If you want to pick a different mnemonic device, go for it, but you do need to know the diatomic molecules, and those are the atoms that form diatomic molecules. Hey, Zig, go up, buddy. He's getting a drink of water first. That's my puppy. You want to see my puppy? We're going to take a puppy break. Oh, he has to go downstairs and go outside. Maybe he'll come back later. Okay. Type of reaction, objective, FGH number 1. I'm on it. FGH number 1. Wait, wrong sheet. How to draw these, or all right, I will just draw them for you. Can I just draw on this thing? Calcium chloride, silver nitrate. So calcium chloride, silver nitrate. Calcium chloride is aqueous when dissolved in water. I can know that by my solubility chart, so that means I want to show it as ions. I have 2 chlorine ions for every 1 calcium ion, so there's that. Then I want silver nitrate. Now silver nitrate is also aqueous in water, so I'd want to show those as separate ions. And when they react in solution, they're going to create silver chloride and calcium nitrate. By looking at my ions, I need 2 nitrates for every 1 calcium, 1 silver for every 1 chlorine. If I use my solubility table, I'll see that silver chloride is actually a solid, and calcium nitrate is aqueous. So when I draw it, I want to show my silver chloride sitting at the bottom, and my calcium nitrate is floating around up top. Now this isn't technically a balanced equation, but this would be like the minimum that I'd want to see. I'd want to see that silver chloride is a solid that kind of sits at the bottom. That's where solids usually sit. Can they float around? I guess supposedly. So as long as you have silver and chloride hooked up together and not showing any ions, then you're good. And calcium nitrate is aqueous, so it's got to be floating around. And I do definitely need to show that there's 1 calcium for every 2 nitrates because that is the ions that they have. Okay. I think I got to the bottom. Woofda. That was a lot of questions, folks. Hi, Zigaroo. You can see my puppies. Oh, wait, come here, Ziggy. You can be on TV. Why isn't this working? Hey, Marley. Hey, Ziggy. You're on TV. There's your, what is it, like a claim to fame? Don't you get like 5 seconds, 15 seconds? Minutes, 15 minutes of fame. That was not 15 minutes for Ziggy. Marley, don't drink all the water. I answered all my questions. That was a lot. I think that's all I got. Hey, Marley May. Hey, little May. Don't drink too much too fast, okay? Okay. Yeah. And it's like a few minutes delay, so I want to make sure they're not late. Because right now they're probably listening to me. Then they'll see my puppies. You smell like dog.
Yes, you do. You're not recording.
I am recording. For precipitate line, my periodic table said it was. It's okay, buddy. You can drink more water now. You just gotta take a break. Okay. Want to be on TV somewhere? I don't think you're on right now, buddy. Yes, I know that the phosphate's the wrong charge. Oops, at the top, but it is at the bottom. Oh, Marley May. Oh, you're welcome to that person. I gotta thank you. That's very kind of you. I'm gonna go to bed now. You should all go to bed. Did you burp on me? No? Okay. Okay, good night all. I'm closing down shut. This is my wave. Marley, give me a wave. We're gonna go out looking at Marley. Can you look at the screen, buddy? No? Good night.